just like people, have organization and maintains balance. Earth is composed of different elements essential for the survival of every living individual. What are these elements essential for our survival? How is this balance achieved? What impact does it entail to every living organism? These are just some of the questions we will answer as we discuss Biogeochemical Cycles. Biogeochemical cycling is the cycle of nutrients between living and non-living components of the ecosystem, creating balance and continuity. Analyzing the word, bio meaning living, geo pertains to rocks and soil, and chemical pertaining to different elements and its processes. There are two types of biogeochemical cycles: gaseous and sedimentary. Gaseous cycle involves processes of most important gases in life: nitrogen, oxygen, and carbon dioxide. On the other hand, sedimentary cycling is composed of soil, rocks, salts, and minerals. This cycle involves weathering by different forces of nature like wind and water. Gaseous and sedimentary cycling are both affected by water cycle through their movement in the ecosystem. Thus, water is an important medium in biogeochemical cycling. The cycling of water in and out of the atmosphere is a significant aspect of the weather patterns on Earth. Knowing where it rains, how much it rains, and the character of the falling rain, snow, or hail allows scientists to better understand precipitation's impact on streams, rivers, surface runoff, and groundwater. Frequent and detailed measurements help scientists make models and determine changes in Earth's water cycle. The water cycle describes how water evaporates from the surface of water, rises into the atmosphere, cools and condenses into rain or snow in clouds, and falls again to the surface as precipitation. Precipitation is a vital component of how water moves through Earth's water cycle, connecting the ocean, land, and atmosphere. The water falling on land collects in rivers and lakes, and porous layers of rocks. Much of it flows back into oceans, where it will win a nest or moves downward through openings in aquifers under the ground. Some places receive more precipitation than others do. These areas are usually close to oceans or large bodies of water that allow more water to evaporate and form clouds. Other areas receive less precipitation. Often, these areas are far from water or near mountains. As clouds move up over the mountains, the water vapor condenses to form precipitation and freezes. This shows a day in the life of water cycle. The sun rises, begins to heat the oceans, lakes, and rivers, and provide energy for plants to give off water vapor through transpiration. The vapor rises to the atmosphere to form clouds, which can be moved by the wind over long distances, and eventually resulting in rain or snow. That precipitation infiltrates into the ground or runs off the land to return to the ocean. All living things are made of carbon. Carbon is the fourth most abundant element in the universe and is absolutely essential to life on Earth. Every organism on Earth needs carbon either for structure, energy, or, as is the case of humans, for both. Because the Earth is a dynamic place, carbon does not stay still. In the atmosphere, carbon is attached to some oxygen in a gas called carbon dioxide. This is used alongside the sunlight to make their own food for growth. Whenever humans burn fossil fuels, most of carbon quickly enters the atmosphere as carbon dioxide. The movement of carbon between the atmosphere, oceans, biosphere, and geosphere is what we call the carbon cycle. Biology plays an important role in the movement of carbon between land, ocean, and atmosphere through the process of photosynthesis and respiration. Virtually all multicellular life on Earth depends on production of sugars from sunlight and carbon dioxide. The metabolic breakdown of those sugars produce the energy needed for movement, growth, and reproduction. Plants take in carbon dioxide from the atmosphere during photosynthesis and release carbon dioxide back into the atmosphere during respiration. Carbon dioxide is a greenhouse gas and traps heat in the atmosphere. Without this and other greenhouse gases, the Earth would have been frozen.
Oxygen is one of the most important elements required to sustain life. It is part of the air human beings and other animals breathe and the water they drink. There are two main sources of atmospheric oxygen. One is the breakup of water vapor. This process is done with the help of sunlight. The water molecules are dissociated to produce hydrogen and oxygen. The second one is through photosynthesis, where plants use sunlight to synthesize simple sugars and oxygen as a byproduct using carbon dioxide and water. This process is done by the photosynthetic autotrophs. Oxygen is produced and is consumed by autotrophs and heterotrophs via cellular respiration. Photosynthesis and respiration are reactions that complement each other. They alternate the release and use of oxygen. These processes balance the oxygen accumulation in the atmosphere. There are instances when oxygen is taken out of the cycle. This is because oxygen is reactive, meaning it can combine to nitrogen, iron, and other minerals to form different oxides. And with these oxides, they stay in the atmosphere. Nitrogen, a naturally occurring element, comprises 80% of the Earth's atmosphere. It is an important building block of proteins, nucleic acids, and other constituents. It is essential for growth and reproduction. Nitrogen is available to plants in two chemical forms, ammonium and nitrate. But nitrogen in the Earth's atmosphere is in the form of N2. But plants have adopted ways in order to utilize nitrogen. Nitrogen enters the ecosystem in two ways. One is in atmospheric deposition, where nitrogen is readily available for the uptake by plants. Examples of these are rain, snow, cloud or fog droplets, aerosols, and particulates. The second pathway is nitrogen fixation. It splits nitrogen into two atoms of free N. The free N then combines with hydrogen to form two molecules of ammonia. This pathway can be done in two ways. One is the high-energy fixation, like cosmic radiation, meteorite trails, and lightning. They provide the high energy needed to combine nitrogen with the oxygen and hydrogen of water. The resulting ammonia and nitrate are carried to the Earth's surface in rainwater. Ammonification is a process that breaks down proteins in dead or waste organic matter to form ammonia. This process is carried out by a variety of microorganisms. It helps maintain healthy soil for growing plants. Nitrification is an aerobic process where some bacteria change ammonia to nitrite while others change nitrite to nitrate. These bacteria are Nitrosomonas, which oxidizes ammonium to nitrite, while Nitrobacter oxidizes nitrite to nitrate. Denitrification is an anaerobic process where bacteria convert nitrate back into nitrogen gas. An example of bacteria that can undergo this process is the Pseudomonas. These conditions are common in wetland ecosystems and open water aquatic ecosystems in the bottom sediments. Processes in the nitrogen cycle are mediated by bacteria. It is influenced by various environmental conditions like temperature, moisture, and the soil pH. Humans have greatly affected the global nitrogen cycle. Major sources of nitrogen through human activities are agriculture, industry, and automobiles. Too much fertilizers naturally outbalances nitrogen fixation and denitrification. Exhaust and combustion from automobile and in industries add up nitrous oxide, nitric oxide, and nitrogen oxide to the atmosphere. And these oxides can stay in the atmosphere for almost 20 years, and when ultraviolet light hits them, the nitrous oxide is reduced to nitric oxide and atomic oxygen. The atomic oxygen can react with oxygen in order to form ozone.
The sulfur cycle has both sedimentary and gaseous phase. One way sulfur enters the atmosphere is through volcanic eruptions. The eruption of Mount Pinatubo, for instance, released at least 5 zillion grams of sulfur. Another way is through the exchange of gases at the surface of the oceans. Dimethyl sulfide is the major biological processed gas emitted by oceans. Gases released by the composition and the combustion of fossil fuels also contribute to the entrance of sulfur to the atmosphere. Usually, sulfur enters the atmosphere as hydrogen sulfide interacts with oxygen to form sulfur dioxide. The atmosphere contains sulfate particles as well that becomes part of dry deposition. Gaseous forms of sulfur, such as sulfur dioxide, is soluble in water. Hence, it is carried back to the surface with rainwater as weak sulfuric acid. This gaseous phase permits the global circulation of sulfur. In its soluble form, plants absorb sulfur where it is used in its various metabolic processes. From these primary producers, it is transferred to other organisms. Death and waste products from creatures then transfer sulfur to the soil and to the bottom bodies of water. Some bacteria, like the green and purple sulfur bacteria in salt marshes and mud flats, convert hydrogen sulfide during photosynthesis to sulfate, which is taken again by plants or other bacteria. Humans also play a vital role in the circulation of sulfur. For example, sulfur in pyritic rocks suddenly exposed by human activities discharges sulfuric acid, ferrous sulfate, and other sulfur compounds. These compounds are discharged in aquatic ecosystem and destroy aquatic life by acidification. Phosphorus is not very abundant in the atmosphere. Hence, it can only follow the water cycle from land to sea. Because of this pathway, phosphorus is not returned to the ecosystem via the biogeochemical cycle under undisturbed natural conditions. The main reservoir of phosphorus are rocks, dead organic matter, and natural phosphate deposits like guano and other fertilizers. But lately, industrial phosphorus have been contributing to the phosphorus cycle as well. In most soils, phosphorus available to plants consists of only a small fraction, and the major process regulating phosphorus availability for net primary production is the internal cycling of phosphorus from organic to inorganic forms, a vital form of nutrient cycling. Most animals gain phosphorus from their diet, particularly from plants. The available phosphorus in the terrestrial ecosystem then escapes to lakes, seas, and other bodies of water. Organic phosphates are taken by all forms of phytoplankton, which are eaten by zooplankton and detritus feeding organisms. The inorganic phosphorus they excrete are again taken up by phytoplankton, whereas the organic phosphorus are utilized by bacteria. When microbial grazers eat these bacteria, they excrete phosphates that are deposited partly in shallow sediments and partly in deep water. Phosphorus tends to sink, thus, deep waters are usually saturated for a longer period of time compared to surface waters. Upwelling results to the surfacing of these phosphates and are again eaten by phytoplankton, driving the marine and fresh water into the phosphorus cycle again. Phosphorus from the sediments of bodies of waters are also taken up by the surrounding and are deposited once again in terrestrial ecosystems. Although phosphorus is transported airborne through soil dust and sea spray, the global phosphorus cycle has no significant atmospheric content. Although nutrients may be passed from one organism to another through various interaction, inevitably, some of these nutrients will be lost to the abiotic components of the ecosystem. Biogeochemical cycles are then crucial to the flow of nutrients from the non-living constituents back to the living organisms. Without these cycles, most nutrients will only stay at one part of the ecosystem, making them unavailable for the organisms that require such nutrients but do not have the means to get it due to its location. Thus, biogeochemical cycles are the natural ways of the ecosystem to renew and pass on the numerous nutrients the whole biosphere contains. Unfortunately, natural systems have already been degraded and disturbed all over the world, altering the normal process of biogeochemical cycles. For example, one cause of global warming is the abnormal concentration of carbon dioxide in the atmosphere. Because of the continuous addition of carbon dioxide to the atmosphere due to human activities, even the carbon cycle could not keep up and balance the flow of carbon within ecosystems. Another human-caused alteration is the dramatic increase to the rates of nitrogen deposition. Although nitrogen oxides do not stay in the atmosphere for long periods of time, they tend to be deposited in places where they were emitted, causing a wide variation among geographic regions. Initially, nitrogen deposition acts as a fertilizer, increasing net primary productivity. But as water and other nutrients become limited relative to nitrogen, the ecosystem reaches the point of nitrogen saturation. When nitrogen supply continues to increase, it may lead to forest decline and soil acidification, altering once again the natural state of the ecosystem. Today, the world's ecosystems are ultimately being challenged. Many disasters may not have occurred naturally if it wasn't for the globe's changing environment. Surely, the biogeochemical cycles are a big part of this changing environment, as it also drives the exchange of nutrients between ecosystems. What is most boggling about this is that we, humans, are a big constituent on these ecosystems, yet we ourselves are the ones altering it to the point of no return. In the words of Pope John Paul II, it may be because of a lack of due respect for nature by plundering of natural resources and by a progressive decline in the quality of life, especially for life that is not ours. We cannot interfere in one area of the ecosystem without paying due attention both to the consequences of such interference in other areas and to the well-being of the future generations. The complexity of ecological question is indeed evident to all. Thus, it is in our hands that we must face today's ecological crisis.